Hi, and welcome to my talk, Dungeons, Dragons, and Graph Databases. My name is Guy Royse. I'm a developer advocate at Redis Labs. There's only really two bits of data on this slide that you need to know. One is there's my Twitter ID. I'll post stuff I'm doing online on Twitter there. So if you want to follow and keep up with what I'm doing, give me a follow on Twitter. And the URL you actually care about, github.com/Guy Royse. That's the place where all the code for this talk is going to be at, along with all the code for all the other things I do. So go out to GitHub and check that out. You can check out guy.dev if you want, but it just has my out-of-date blog. That's not super important. But I'm a developer advocate. But in addition to that, I'm also a player of Dungeons and Dragons. And I've been playing D&D since I was a kid in the 80s. And so I thought I'd include my character sheet here. Here I've got my name and my alignment. I felt like neutral good was a happy balance between law and chaos. I've got my class, Bard, which is the closest thing to developer advocate that I could find in the player's handbook. And I've got my ability scores here. And so you see I've got sort of mediocre physical attributes. And in my mental attributes, I'm not very smart and I'm not very wise, but I'm really charismatic. And so that gives you an idea of what the talk's going to be like. I can look smart, even though I'm not actually smart. So, but as a D&D player, I've got a problem. And that problem is that I want to optimize my dungeon crawl experience. I need to go into the dungeon, explore all the rooms that are in it, find the monsters and kill them to get their experience points so that I can become more powerful, and gather the treasure so I can upgrade my gear and defeat more powerful enemies. And I want to do this in the most efficient manner possible. I want to find the best paths through the dungeon that have the best treasure and the best monsters. So how am I going to do that? Well, in addition to being a D&D player and a developer advocate, I'm a developer. I can write software. And so why don't I build a database to solve this problem and go through this graph or through this dungeon, right? And find the best rooms and the best treasure and the best monsters. And so I'm like, I could do this with a relational database with the rows and the columns and the tables and the joins, or I can use it with a graph database, which is what we're going to talk about today. If you haven't looked at graph databases are really cool. And if you haven't looked at graph theory itself is kind of interesting. So let's ask the important question. What's a graph database, right? We're gonna build a graph database of this dungeon, and we're gonna build a relational database of this dungeon, and we're gonna show how to query them. And so by contrasting these things in this talk, we're gonna learn about graph databases. So what's a graph database? It's actually the wrong first question. The first question is, what's a graph? A graph is a sort of a mathematical abstraction of nodes and connections, or vertices and edges. This die 20 here is a graph. It has a vertice, which is the point on it. I have a physical die 20 here as well, right? So you got that point there. And then the edges are the things that connect the vertices. And, this is the mathematical abstraction. In this case, this graph is representing a Platonic solid, a 20-sided die isohedron. However, they can represent other things like perhaps a series of nodes or of roads, right? A transportation network. The intersections are vertices and the roads themselves are edges. Or it could represent, a social graph where the vertices are people and the edges are their relationships, the nodes and the relationships, the nodes and the connections. Or it could even represent like a genealogy relationship where you have, people being related to each other by blood. And so the graphs can represent all these sorts of structures. The simplest graph is what's called a null graph. It's a graph that has, nothing in it. It's kind of boring, right? Some people argue whether a null graph is actually a graph or not. But I think that's sort of like arguing about what the value of undefined is in JavaScript. It's still nothing, right? And so to make the graph a little more interesting, let's add some nodes here. And so now we've got this graph that's all nodes, all vertices, but no relationships, no connections. It's just a bunch of points floating in space. And so this can be useful, right? This represents individual things, but it's not super useful because there's no relationships between them. So if we can add some relationships to the graph, now our graph gets to be a little more interesting. It looks a little more like what we think of when we think of what a graph is. So here we have, nodes A and D are related to each other. They're connected. There's an edge connecting them together. A and C are connected, G and C, etc. But not all the nodes are connected to all the nodes. And in fact, there's a term for that, and that term is isolated. So node E is isolated because it's not connected to any other nodes. But it's not just nodes that can be isolated. Subgraphs can be isolated. Nodes B and F are related to each other, but they're not related to the larger graph. And so they're isolated as well. And of course, that means that even the big center section, which we would think of as being the big part of the graph, it's isolated as well because it's a subset of the graph. It's a subgraph. And so this is an idea of how we talk about graphs. Portions of them can be isolated. And in a graph database, portions of your database can be isolated. And that's okay. It's still a perfectly valid graph. But we're going to go ahead and connect all the nodes in some fashion or another. So now this graph is referred to as being connected. And this doesn't mean that every node is connected to every node directly, but it means that every node has a path to every other node. So I can get to F from D by way of A and B, or A, C, and B, or even, well, there's probably a couple paths there. I could even loop around, but there's paths that connect these nodes together. And so this is a connected graph. I don't have a picture of it in my slides, but there's also a fully connected graph. A fully connected graph shows, you've seen them before. It's a ring of it's a ring of nodes, and everyone connects to every other node. The picture is often used to describe what a network is. So that's a fully connected graph. This graph that we've been looking at is undirected. And so this means that the connections bringing them together don't have any direction. There's no additional information about the relationship. We just know that A and B are mutually related. We don't have any idea to how that relationship works or in what direction that relationship goes. And so that's like saying that I am related to my mother and my mother is related to me. That's undirected. A directed graph is going to say this relationship has a direction and it's intrinsic to that relationship. So my relationship with my mother has a directionality to it. My mother bore me, not the other way around. And so there's a one-wayness to it. And so directed graphs can represent these sorts of things. This could be a one-way road in a transportation network, or it could be a corridor in a dungeon, right? That only goes one way. Maybe it's like a slide trap. You slide down it, and so you can only go down it, but you can't go up it. But it represents that sort of one way. There's some directionality to it. Graphs have degrees. Well, nodes within graphs have degrees. And so the degree is the number of relationships that a node has. So a node A in this graph has a degree of 3 because it has 3 relationships. One to B, one to C, and one to D. You can also be a little more specific about them and talk about out degree. That'd be how many outgoing relationships it has. And you could talk about in degree, which would be how many incoming relationships it has. So node B has an out degree of 2, an in degree of 1, and a total degree of 3. So these are ways we can talk about graphs. These nodes have degrees. And, this is a nice, tidy little graph that I've created here, but graphs can connect to anything and anywhere. There aren't really any rules about how you wire these things up. So nodes can connect to themselves. As you can see here, node A connects to itself. Nodes can be directionally mutually connected. So A connects to C and C connects to A. They can have multiple parallel ones as well. A can connect to C multiple times. And so there's really no rules. And even this graph is neatly printable on a 2-dimensional surface. But they don't actually have to be 2-dimensionally bound. If you think about a graph representing this 20-sided die right here, if you tried to draw that on paper, it loops, right? It creates a 3-dimensional surface because of how you have to put it together. And so that doesn't matter. They can be as many dimensional as they need to be. It almost doesn't matter. It's just showing the nodes and the relationships. A graph database, which is what we're here to talk about, is what you get when you overlay data on top of the structure. So here, these nodes aren't just these lettered nodes that we know about, A, B, C, and D, and all the way through F or G, whichever letter it was. They represent rooms and monsters and treasure in our dungeon. And we can hang data off of those nodes. So not only do these nodes have a label, this is a room, this is a treasure, this is a monster, but it has attributes associated with it as well. The room has a name. Room 1 is the statue room. Every good dungeon starts with a statue room. Monster 4 is Alice the elf. It has a name and a challenge rating and experience points. And the relationships themselves can also have data associated with them. They can have a type. A leads to type means this room leads to another room. It has a corridor connecting them. Or contains. This room contains monsters and treasure. And so we've laid data over top of the nodes and over top of these relationships. And that gives us a database worthy of Mordor. So some rules for graph databases, sort of a summary and just to crystallize some of these things I've talked about. You've got nodes and relationships. The nodes represent items. They're things. They tend to be nouns. They can have labels. They can have more than one label. So a node could be both a room and a chamber, shall we say. And they can have attributes, of course. The diameter of the chamber might be an attribute. The name of the room is an attribute. And they can stand alone. Just like in a graph, nodes do not have to have relationships. They can just exist out there as a point in space. Relationships represent connections between the two nodes. So the room contains a thing. They tend to be verbs, and they have a type and they have a direction. And so a room containing a thing is different than a thing containing a room. So the directionality of this matters. And they can have attributes as well. But most importantly, they can't exist without nodes. If you delete a node, any of its relationships go away. It turns out you need two to have a relationship, right? And that makes sense if you think about it, because if you think of nodes as being points, the relationships are kind of like lines. And you need 2 points to determine a line. So if you delete a node from a graph database, the relationships to it disappear as well. And they end up reading kind of like sentences. So portions of your graph will read like a sentence. The room contains a monster. So the room is our subject, the monster is our direct object, and contains is the verb that links them. So transitive verbs specifically. So that's the theory. Let's go in and look at stuff in a little more detail. Let's make some of this stuff real. So, because we've still got a problem. Well, I've still got a problem. I still want to figure out the best path through the dungeon to find the monsters and to find the gold. And I'm going to do it with a relational database, and I'm going to do it with a graph database. So when it's time to talk to these databases, I'm going to assume that you've done a little bit of SQL and you're familiar with relational databases. It's one of the assumptions kind of baked into this talk. If you haven't done a lot, don't worry. The graph pieces are still totally relevant, but the comparison makes it a little richer. But when we talk to a relational database, we use SQL. And so we, select from tables with a filter of some sort, or we insert into a table with the values we want to put in there. Right. This is SQL is actually one of the few languages I learned in college that I still use on a regular basis. So it's pretty ubiquitous. So yeah, SQL is how you talk to a relational database. Cipher queries are the language used to talk to graph databases, or some graph databases. There are other languages as well, but Cipher is a popular one. It's the one Redis Graph uses, and it's the one that was created by Neo4j and open sourced and given out to the community at large. And Cipher queries, well, they query graph databases. And at the heart of a Cipher query is this idea of matching. So if we look at this little matcher underneath our picture of a graph, it shows what looks like a cross between ASCII art and a query language. You've got these little round things which match nodes. And if you look at how we've been drawing our graphs, we draw circles for nodes. You've got these parentheses which sort of suggest circle, round, right? It's the node thing. And so this matches a room node and a monster node. And then this bit in the middle matches a relationship between them. And you can see the matching syntax actually has an arrow, right? If we look at it, you can see it's got a little line there and it's got a little greater than that says this is an arrow. And so it's kind of like ASCII art, but it's also a query. And what this will do is this can be used to match this pattern in the graph. So going through the entire graph, find rooms that contain monsters, and then we can do things with them. But this pattern will match. And it walks that entire graph and finding all the instances of all the portions of that graph that match that pattern. So let's go for the CRUD operations: create, read, update, and delete on graph and SQL. So in a relational database, presumably you've got a rooms table. And so to create a room, you insert into the rooms table. To do this in graph, to create a record, there is no table. There is a big void of nothing. We have a null graph, and we're going to create a node using the create command. And so we say create r:\room in parentheses. And so we're saying create a node. And we're saying give it a label of room. That's what the :room means. Assign it to the variable r. And then in the set that we have after that, we can do things to manipulate that room. We don't need the set. If we want to just create a node with the label of room and no properties, that first line's enough. But the next set of lines lets us go in and set the ID to 1 and the name to statue room. These attributes are arbitrary. We can make them anything we want because there's no schema, unlike with a relational database. So that's creating a node. Next, we want to read that node out. You have to have the thing to read before you can read it. So we create, then we read. And here we got the ever popular select statement. We've done these a million times. Select columns from room, from table, where, filter. For the equivalent thing in graph, in Cypher, we want to match a node pattern. So we want to match a match pattern. And so here we're matching a room, all nodes that contain with the label of room, assign it to that variable r, and we'll use a where clause to filter it out. So we only want to look at ID 1, and then we return it. Now, these first two lines here in this query, the match and the where, are going to repeat in the next, in the updating and the deleting. We're just going to change the things we do with them. So here we've matched it, and we filtered it, and we returned it. But if we want to update a room, then in SQL, we use update. But in graph, we instead say set. So we can match that room, filter it, and then set it using a syntax very similar to how you would do that in SQL. We set the name to statue hall. The room is getting an upgrade. It's getting more statues. Deleting, again, is very similar. Here we've got the most dangerous command you can enter in a relational database: delete from rooms. If you don't put that where clause in there, you're going to have a bad day. In graph, again, we match all nodes where the label is room and assign them to a variable r. We filter and get just the room we want. And then instead of returning it or setting things on it, this time we use the delete word. And so we delete it. So create, read, update, delete. This is your real basic node manipulation in Cypher. So a note on this, I've been using this syntax where I match a node and then I give it a filter. But you can actually use curly braces on your node as well and say match a node with a label of room and has properties of ID with a value of 1, comma, name with a value of something else. And so this actually is the syntax for the stuff between the curly braces is the syntax you would use in JavaScript. They act, of course, in an and relationship. It says match in the graph everything that is of this type has a label of room and has an ID of 1, and this will return match all those nodes. And you can use the same syntax when you're creating as well. Here we're doing a set, but you can just create with a couple of curly braces and then the attributes or the properties that you want on that node. So this is alternate syntax we can use to do the things we've been doing. And here I'm going to kind of show that in use here. Here we're creating a monster. And you'll notice that we did not assign monster to the variable m. That's not a typo. We don't need to refer to m because we're defining all the properties on there. We're not going to call set, so we don't need it. Here we're creating treasure, and we're using a hybrid one. So treasure T, we set the ID and the gold piece value as part of the node creation. And then we use the set command to actually set the name of that to a +1 sword. So cool. This is sort of a super quick intro to Cypher syntax. This is what our relational database looks so far. We've got isolated tables with rows. Our graph is a bunch of isolated nodes. There's no relationships at all. So let's take this a little bit further. Let's put a monster in a room. And if we're going to do that with a relational database, if we're going to relate the monster to the room, we first need to alter our table. So we alter the table monsters and add a room ID column. So this monster can be in this room. We're creating a foreign key. And then once we've altered the table thusly, we can update our table to reflect where that monster lives. So Alice the elf is in room 1. Bob the ogre is in room 3. How do we do this with graph? Well, we're going to establish a relationship in graph. And we do that by using multiple matches. So our first line here matches the room that we want to use to put the monster in. And we give it an ID of 1. And then we match the monster. And we assign these to R and M. And then we create a portion of the graph where we are using R and M and the relationship between them. And so this will create that relationship. So now the room contains a monster. And it's all in this magic create. These will not be created because they already exist, because we've matched them already. If we decided to try and put attributes on here and stuff, it will create new ones. So be careful with that. But as long as you reference just a variable here, it will not create a new one. To put a treasure in a room, we use that same pattern. We alter the treasure table. We update the treasure table to place the treasure in the room. It's just like with monsters. And again, with graph, it's exactly the same pattern again. So we match the room, we match the treasure, and then we create a relationship between them using the create command. And so if we look at our graph, or look at our relational database now, we have a one-to-many relationship from rooms to treasures and rooms to monsters with that foreign key. And our graph now has some relationships as well. It's showing that this room 1 contains Alice the elf, and room 2 contains a +1 sword. I think I want to go to room 2. First, get my +1 sword, and that will help with Alice and Bob. And so this is our graph so far. There's some relationships, but we still haven't done the best we can do. We still need to create relationships between the rooms, and we'll get to that in a bit. But let's look at a couple queries that we can do against this first. So because it's Munchkin time, we're going to find the rooms that have the best monsters and the rooms that have the best treasure. And to do that with SQL, we need to do a join. So here we're going to select the columns we care about from the tables that we care about and say where this foreign key equals the table equals primary key. And then we can sort that. To do that in graph, we just do a match. And so here's the room contains the monster that I talked about at the very beginning of Cypher. We can match in the graph the pattern of a room with a relationship of contains to a monster. And it will scan the entire graph and find all of those instances and then return them. And then we can return properties on these things. So here we're returning the ID, the name, and the experience points. And then we'll go ahead and order that by experience points so that we can find the room that has the most powerful monster so we can get the most XP. And it's the same thing for getting all the gold, same join, just different nodes. Here, instead of having that contains relationship with a monster, it's with the treasure. Instead of the experience points, we're looking for the gold piece value. But it's the same query. We're matching the room contains a monster and then returning things from it, which is cool, but not cool enough. We need to take it to another level. We need to connect the rooms and then do queries of paths through the graph that involve things of the same type. So how would we connect the rooms together for a graph or for a relational database? Well, we need to create a many-to-many foreign key table, a self-referential table. I can't remember what we call these things off the top of my head, but the idea here is this is a table that says this room is connected to this room. In many ways, it's a table defining a graph. And so we create this table. It's got the from and the to, saying this room connects to this room. And then we insert connections into it, linking those rooms together. This is a little bit different than what we've done with the other ones, because before we'd add a foreign key, here this table is nothing but foreign keys. It maps that many-to-many relationship. To do it in graph is actually no different than any other relationship. Instead of matching a room and matching a treasure, we match a room and we match another room. And then instead of creating a relationship from a room to a treasure, we create a relationship from a room to a room. And so it's exactly the same syntax. The graph doesn't care that these nodes are both labeled room. There's no schema, so it doesn't matter. We can wire these things together any way we want, easily with the same syntax. And so here's our relational database so far. It's gotten a bit involved. We've got rooms and treasures and monsters with with one-to-many relationships, and we've got a many-to-many relationship of the rooms to themselves. Our graph database actually kind of looks like our dungeon map. We've got 3 rooms that are connected together. They've got things that are in them, and yeah, it looks kind of cool, doesn't it? So now that we have this graph, we can do some really interesting queries that are difficult to impossible to do with SQL. And so I'm just going to talk about the Cypher versions of them. It's super munchkin time. And the key to making these pathing queries, where we can find interesting, more sophisticated queries, is the variable length relationships. Is this little bit here. So room 1 and room 2 are just matching. And then that star means match multiple leads to relationships. So this would match on the room leads to a room, and the room leads to a room, which leads to a room, and the room leads to a room, which leads to a room, which leads to a room, which leads to a room, et cetera, ad nauseum. And so it matches one or more hops to get to that room. And so that's really powerful because we can walk that graph and find the pattern of every room connecting to every room, and every unique path that can do that. You can, obviously, if you have a big graph, you might not need to go 10 hops out. Maybe you want to just find things that are a little bit closer. And so you can limit that and give it a minimum number of hops and a maximum number of hops. And so this will find things that are 1 hop up to 3 hops away and in between. So 1, 2, and 3 hops away. So this finds nearby rooms. Right? So we could use that to find rooms that are next to us. So if we're in room 1, right, match room 1 right here. Match a room with an ID of 1 that leads to 1 or 2 rooms away, another room. So give me a list of all the rooms that are 1 or 2 rooms away from the room I'm currently in the graph. And then return their ID and their name. So this gives me a list of places I could go next. It's kind of interesting, but let's make it a little more interesting. Let's find the nearby rooms with the most gold. So here we're matching a room with an ID of 1 that leads to, it's the same query as before, right? The room we're in to another room that contains treasure. So we've got a more sophisticated match here. And then return those values, including the gold piece limit, or the gold piece value of the treasure, and then limit it to 1 so that I get the biggest one floats to the top of the list because we're order by here, and then we limit by 1. We can find the longest path through the entire dungeon by matching rooms lead to rooms with a star and assigning it to a variable here. We can take those paths that it queries here and assign it to a variable, and we ask questions of those paths. And we can get a list of all the nodes that are in the paths. We can get the lengths of them. We can order them. We can limit them and find out which is the longest path through the dungeon so that we can hit every room. We can find the room with the biggest treasure. So here we've got this idea of width. We can do a match and then do aggregation where we say width max of a particular property and assign that to a variable to use later. And so then the next match, we can use that max GP and assign it down here as a way of saying, give me the room that contains treasure where the gold piece is equal to max GP. And this will give us the top room or rooms if there's a tie in the gold piece value. And we can even combine these all together into one monster query, which does this gold piece matching thing here, finds the biggest room, then finds all the rooms that have treasure, and returns the one with the max gold piece value, then finds the path from the room you're in, start room, and to the stop room, and then gives us the shortest path. So we can do really, really complex queries against Cypher, and there's a lot more that you can do with Cypher beyond this. I'd love to do a demo, but I believe I'm already up against my time limit. So I'm going to pass on that, but there's lots of code out on GitHub. You can go play with it yourself. It's all using Redis Graph and a bunch of JavaScript to generate a random dungeon, and you can go in and query it or run queries against it. So lots of fun. Practical applications, I kind of hit it on them earlier. Social networks, genealogy, transportation networks, and logistics are all great candidates for it. They're naturally graphs. Here's a quick list of resources if you want to go deeper into playing with graph databases. You got redis.io and redisgraph.io, so you can play with Redis Graph. I like to use Docker to do this, but you can also use Redis Enterprise Cloud. If you want to learn the ins and outs of the Cypher query language, Neo4j's got a list of that, and the opencypher.org has that as well. And I've got a blog post I wrote about Redis Graph, which has some of the things that are in this talk. I work for Redis. Go check us out online. We got a Discord server. I'm always on there. You can ask me questions. We got a bunch of free classworks and YouTube videos on these sorts of topics. And you can sign up for Redis Enterprise Cloud for free and try out Graph on that as well, as opposed to installing it on your computer. Here's a QR code that will take you to the slides and the code and 3-6 plus 2 pull requests. I promise that this QR code will never give you up, nor will it let you down, nor will it run around or hurt you. So you can totally trust it. It takes you to that URL. And that's pretty much all I've got. My name's Guy Royse, and thanks for attending my talk.